Good afternoon, all. So, in the last class, we have discussed that is the differential instrumentation amplifier using Tranducer bridge. So, why we are using the differential or instrumentation amplifier here? Because some of the transducer will not have a strength to drive the output devices. Output devices may be a meters or display units. So, in order to make the strength of the or that is the transistor output, we are going to use this instrumentation amplifier. Okay, we have seen. So here the physical quantity that is to be measured is changed. Then the resistance of the transducer will change. So then that is passes through the voltage follower. So then that is given to the differential amplifier. So and output of the differential amplifier is given to the meter. So that meter will give the how much your physical quantity is. So this is we have seen that is the bridge is balanced when VA is equal to VB. So bridges when bridge is not balanced, that is when you are going to change the physical parameter, bridge becomes unbalanced and the RT that is resistive to undo the resistance becomes RT plus delta R. We have seen this is going to be bridge balance equation. So next we have seen when the bridge is unbalanced, that is the physical quantity is changed. So then the transducer resistance is changed. So then we have seen VA is changed and VB remains same, and VAB we have calculated. So then we have given to the output, so that the differential amplifier output. So V naught is equal to VAB into RF by R1. RF by R1 is a gain. So then V naught is going to be this expression. Okay, so this we have seen. So before going to this temperature indicator using thermistor, so yesterday we were discussing a problem. So I will take up the problem. We have to see here the case of okay, so that is the same circuit you have to refer for this. In this R1 they are given RF, RA, RB they are given, and the supply voltage is given, and pump supply voltage is also it is given. Okay, so they have given RT 120 kilo ohm at a temperature reference of 25 degrees Celsius. And they are given temperature coefficient resistance minus 1 kilo ohm per degree Celsius or 1% per degree Celsius. Determine the output voltage at 0 degree and 1000 degree. Okay, you have to determine the output at 0 degree Celsius as well as so this is 100 degree Celsius. So this kind of problem they will ask in the exam. So how we are going to do? At 25 degree we have a resistances RA, RB, RC. So all the resistances are equal. We are going to say that the bridge is going to be balanced. So that time V naught is equal to 0. So then at 0 degree, delta R, we have to find out that is a change in the resistance of the thermistor. So then delta R is equal to, okay, so this is minus 1 kilo ohm per degree Celsius into 0 degree minus 25 degree Celsius. So this becomes, that is 0 minus 25, that becomes a minus 25. So minus into minus 1 kilo ohm, that becomes a plus 25. Okay, then output voltage. So we are calculating delta R first, then substituting in the V naught expression. So V naught is equal to, so you substitute all the resistor values and you will be getting V naught is minus 1.07. Okay, so next similarly at 1100 degrees Celsius, so calculate delta R. Delta R is minus kilo ohm per degree Celsius. 100 minus so 25, here it becomes 75. So 75 into minus 1 kilo ohm, this becomes minus 75 kilo ohm. So next V naught is equal to, so substituting all this we are going to get 5.7. So V naught is minus 7.01 volt when the meter dial marked as a 0 degree Celsius. So when the it is going to be 100 degree Celsius, V naught is going to be 5.17 meter. So it is 100 degree Celsius, but at 25 degree Celsius, V naught is going to be 0. That is initially it is minus, so then it is going to be 0, then it is going to take a positive. That means at 0 degree, we have a minus 1.7 degree. maybe at 5 degree it is going to be some different value, at 10 degree it is different, 15 degree it is different, and 25 degree it is 0. So then for 35 degree, 45 degree, and it is going to be that is getting the positive values. Okay. Oh, this is the way they will ask, and you have to derive the expression for V naught when they ask, explain that is a differential transducer, differential instrumentation amplifier using this transducer bridge. Okay. There is a temperature indicator. So already we have studied thermistor. Thermistor is a device that is used to measure temperature, control temperature as well as to compensate temperature. Okay, this is going to be resistance transducer. So they are basically semiconductors. So in many respects, thermistor resembles the conventional resistor. So it is usually two-terminal device. So it has a resistance of its fundamental property. It's generally installed and operated in a manner and an ordinary resistor is there. So the great difference is what this thermistor is going to exhibit a NTC or it may be PTC, but what we studied thermistor is a NTC. So most of the thermistor exhibit a NTC. NTC means what? That is as the temperature increases, resistance is going to be decreases. Okay, temperature coefficient is expressed in ohms per degree Celsius. Since it is thermally sensitive resistor, it has a high temperature coefficient of resistance and is therefore well suited for temperature measurement as well as control. So we have to refer the same circuit of a differential amplifier using a transducer bridge. Okay, so the transducer is used is a thermistor. Okay, so it is used to indicate a temperature. The output of the meter can be calibrated to Fahrenheit. The bridge is balanced initially at their desired reference condition. The thermistor also changes unbalance of the bridge, which in turn produce a meter deflection at the output. Okay, by selecting appropriate gain for the differential instrumentation amplifier, the transducer bridge, the meter can be calibrated to read a desired temperature. In this circuit, meter movement depends upon the amount of unbalance in the bridge. We know this, the meter is going to deflect depending upon the amount of unbalance. So which is caused by a change in the value of thermistor resistance delta R. So change in delta R for the thermistor can be determined as follows. So delta R, so it is going to be a temperature coefficient of resistance. So this is going to be is equal to final temperature minus reference temperature. Okay. Hmm. So this is thermistor, that is a delta R can be determined. So it is temperature coefficient of resistance. So this is going to be so final temperature minus reference temperature. So if the meter is in the circuit is replaced by a relay, that is the circuit what we referred. So in that meter was there, it was a deflecting amount of change in the physical quantity. And if we are going to change the temperature according to that, so the resistance will be So resistance is going to be changes if you use a thermistor. So then the meter is going to showing amount of deflection, that is a change of temperature. If you are going to play that meter with a relay, amplifier drives the relay that controls the current in the ETA generating circuit, a temperature controller can be formed. Okay, so if you are going to replace the meter with a relay, then output of the differential amplifier that is going to drive the relay and that controls the current in the heat generating circuit. Okay, so then it is going to become a temperature controller. So that is going to become a this is the way we can make that circuit is going to be a temperature controller, or that is to measure the physical quantity, to measure the temperature. That is the same circuit. If you use a resistive transducers, so that is going to measure the physical quantity. If the physical quantity changes, bridge becomes unbalanced, that you are going to measure through the meter. So if instead of that resistance thermometer, that is the resistance transducer, if you replace that with a thermistor, so then there is a change in the temperature. The resistance changes. According to that, meter will indicate a temperature change. So if that meter itself is going to replaced with a car, that is a relay, so then it is going to become a temperature controller. Okay, so that is you have to practice that problem. So what I discussed in the last class, so that they can change the parameters and they can ask the same kind of problem. So next we will go for a analog weight scale. We are going to refer the same circuit, that is analog weight scale. So for all the temperature indicator using thermistor and that is a differential intermediate using transducer bridge. The same circuit used for this analog weight scale also. So in the circuit, this circuit can be converted into a simple analog weight scale by connecting the strain gauges in the bridge circuit. Okay, so bridge, this bridge circuit is there, no? So this for this bridge circuit, so we can convert this circuit into a and connect the strain gauges in the bridge. Okay, so by connecting the strain gauges, we can replace this differential instrumentation amplifier using transducer bridge circuit into a analog weight scale circuit. The strain gauges are connected in four arms of the bridges. Here the resistance are connected. So instead of this resistances, so all the four arms are going to be a strain gauges. The strain gauges is connected in four arms of the bridge. Okay, so we can see here. That is instead of resistance, all the four arms are going to be a strain gauges. So the strain gauge elements are mounted on a base of a specially made weight platform, so on which external force or weight is placed. Okay, so that strain gauges in the four arms, they are going to be mounted on a base of the specially made weight platform on which the external force or weight is going to be placed. So one pair of strain gauge elements in opposite arms elongates. That is, so if I'm going to say these are going to be a strain gauges. Okay, this is I'm going to say this is going to be and this is going to be a RT2 and this is going to be a RT3 and engages. So they are more than base external force or weight is placed. So then when opposite arms elongates, that is opposite elongates are means what? So here RT1 and RT3, so they are going to be one opposite pair, and this RT2 and RT4 they are going to be another opposite pairs. So this it is going to be elongates. This RT1 and RT2 it is going to be elongates. So elongates means it is going to be, so that is it is extend. extent. So both increases the resistance. RT1 RT3, that is the one pair, it elongates, means RT1 RT3. So both resistance increases. So while other pair, so this pair is there RT2 and RT4. So that is going to be compressed. So this pair it is going to be a compress. So this is going to be compressed. That is in that RT2 and RT4 that is going to be decreases in resistance, or it may be a vice versa. Okay, so the bridge is going to be balanced. Okay, so this you understood. The same circuit we are going to replace, that is a resistor usual largest engages. If that is done a base in such a way that weight is placed or external force is placed on this. So one pair is RT1 RT3 that is going to be elongate, means RT1 RT3 resistance increases. Another pair RT2 and RT4 means that is another pair, in this the compression is going to be happen, the resistance decreases. So here the bridge is going to be balanced when no external force or weight is placed. We are going to say this bridge is going to be balanced when there is no external force or weight is placed. So that means what? So bridge is going to be balanced means, so your RT1 is equal to RT4. All the strain gauges resistances are going to be equal. So that is having the same value R. So then we are going to say the bridge is going to be balanced. RT1 is equal to RT2 is equal to RT3 is equal to RT4 is equal to R, means the bridge is balanced. So that means no weight is applied. Then output of the weight scale is going to be zero. When the bridge is balanced means all the resistance are equal, and the sum of is placed on the scale is placed. So now weight is placed on the scale put from a. So then RT1 and RT3 increases in resistance, and RT2 and RT4 decreases in resistance by the same value delta R. Okay, so if some weight is applied or some external force is applied, so then increases in resistance increases, and this RT2 and RT4 it is going to be decreases. Okay, so by the same value delta R, and the bridge is unbalanced. So therefore, by giving an unbalanced output voltage, we are going to write, so that is unbalanced output voltage here. So that is unbalanced output voltage VAB is equal to E into delta R divided by R. Okay, so VAB is equal to E into delta R by R. So E is a excitation voltage of the bridge, and R is going to be RT1, RT2, RT3, RT4 unstrained gauge resistances, and delta is a change in the gauge resistance. So then instrumentation amplifier, that is a differential instrumentation amplifier, then applies voltage VAB. So this VAB you are going to apply to the instrumentation amplifier, so that giving a deflection on the meter moment, as the gain of the amplifier is RF by R1. So output voltage V0 is going to be, the V0 output voltage is equal to E into delta R by R. This is going to be output to delta R by R. V0 is equal to the gain into VAB. The gain of the amplifier is selected depending upon the sensitivity of the strain gauges and on the full scale deflection requirements of the meter. The meter can then, it is calibrated in grams or kilograms to weight, give the weight. Okay, so in this way way they are going to find out the that is a weight. So that is how much the weight you are applied or way. So when no force is applied or no weight is applied, the bridge is going to be balanced. So when the force is applied, there is a delta RT1 and RT3 increases, RT2 and RT4 decreases. Okay, so that it is going to give. So that is how much weight you applied or how much force is applied. That will be indicated in this meter. So the expression V naught is equal to E into delta R by R into the gain of the instrumentation amplifier RF divided by R1. Okay. You can see here. So this is the way the bridge is going to be connecting. So that is RT1, RT3 that I have taken in opposite. So you can connect in. So that is going to be RT1, RT3 and RT2, RT4. So this is the way they are going to connect the bridge, and it is going to continue to the next circuit. Okay. So next, so this is what E naught is equal to E into delta R by R into RF by R1. So this is the way they are going to measure the weight, okay, or amount of force you are going to apply it. That is going to be indicated in the meter. So this is all about transducer. So next we will move on to that is PLC, that is a programmable logic controller. So PLC, we will see that is a programmable control PLC. Commonly, it's called SIT. So it is a sensitive computer. So it is a programmable logic control that is a logic in India computer. It is a device that was invented to replace the necessary control. So PLC is basically operates by looking at its inputs and depending on their state and turning an output out. User enters the program. So computer is obviously need to so write a program. Okay. So we're going to replace instruction control. So this is okay. So PLCs are used in many, that is machining, not machinery, machining, packaging, material handling, turns on. We want to turn on a solenoid for 10 seconds, turn it off, regardless of how long the switch is on for. Okay, so that is how we are going to replace this relay system. So with this PLCs, so that is the solenoid is there. We have to turn on for 10 seconds, and after that we have to turn off. So next, this can be done simply by external timer. So that is using external timer. So I can turn on the solenoid for 10 seconds. After this, I can turn off. So if this process included 10 or more switches and solenoids, okay, when the switch is turned on, the solenoid is on going to be. So on how long the switch is on? Switch when the switch is on, the solenoid is on. It is going to be on for 10 seconds. After that, is it switch is on or off? So it will turn on. That is solenoid turn on for only 10 seconds. When we are going to switch on this, so then solenoid will turn on for 10 seconds. After this, still the switch is on, so it will off. So if I'm using this can be done using external timer. So but if this process I'm included 10 more switches and solenoids. Okay. So many number of switches are there and many number of solenoids are there. So then we need 10 more external timers. Okay. So but if the process also needed to count how many times the switches individually turn on, so then lot of external counters would be needed. So this is going to become a bigger process and so this can be replaced by the need of a PLC. That is, a PLCs can be simply programmed to count its input and turn the solenoids on for a specified time. Okay, and display circuits are really controls using PLCs. That is, so when switch is going to be switched on, so that time the solenoid I'm using, so that is going to be turned on. It is going to be turned on only for 10 seconds. After 10 seconds, still the switch is on, so that solenoid is going to be turned off. So this can be achieved by using a external timer. If I'm going to use that kind of a solenoids and switches for a 10 and more number of switches and solenoids I'm using, so then more number of timers I'm going to require, so that becomes a bigger process. Then I need a counter, that is how many times each and individual solenoid it is on, so that I need to count. So that going to require a large number of counters. So instead of that, so I can replace that with a PLC. So PLC can simply program, so I can write a program to count its inputs, so and turn on the solenoids, and it is going to be on for some specified time. Okay, since PLC is a computer, you should be told what to do. So then I am doing a programming and it is going to a computer, means I am going to tell the task that this much the task you are going to do. So PLC knows what to do through a program that is developed and then entered its memory. So computer means it will be having memory. I'm going to write a program and store it in its memory. According to that, it is going to do the task. So PLC, however, without a set of instruction is just a black box. Okay. So without instruction. So program means I'm going to write instructions. Set of instructions is going to call a program. So that you have written a C programming, I think. Okay. So PLC, so without a set of instruction is just a black box consisting of electronic components only. Okay. So PLC can control devices such as the limit switches, push buttons, proximity or photoelectric sensors, float switches or pressure switches, etc. to provide the incoming control signals into unit. The incoming signals is called the input. So these control signals or inputs interact with the instructions specified in the user program, telling PLC how you have to react to the incoming signals. So the user program also directs the PLC um, on how to control field devices such as motor starter, pilot lamps, and solenoids. Uh, just a minute. Okay. a signal going out of the PLC control. So that is a control. So that is the control signals are inputs. So that is a input to the PLC, that is called a input. Okay. So then that is a signal that is coming out of the PLC. It is going to be called as an output. So be defined as per National Electrical Manufacturer Association as the digitally operated electronic system. So PLC, it is a solid state computer, so digital computer. So now according to this National Electrical Manufacturer Association is a digitally operated electronic system designed for use in industrial environment. It chooses a programmable memory for internal storage of user oriented instructions for implementing specific functions such as logic, sequencing, timing, counting, and arithmetic to control through digital or analog inputs and outputs. The various types of machines are processors. Both the PLC definition and its associated peripherals are designed so that they can easily integrated into industrial control system and easily used in intended functions. Okay. So this is what the introduction of PLC. So what is PLC? So why we are going for PLC input and what is the output? So next we will go for a PLC structure. So PLC structure is going to consist of a CPU, memory areas,
I think we have repeated the information for the only structures from the only we are repeating. So we are also repeating it once again. One for an external source different 1.5 these values equal to minus 4 integral of initial defining e dot. Now dividing W by what happens? Which gives
so you can see the structure of PLC here. So it consists of a CPU, memory areas. You can see here. Okay. CPU, memory areas, uh, receive input and output data. So PLC is considered a box full of hundreds and thousands of separate relays, counters and timers and data storage location. So PLC, it is going to be a box full of hundreds of thousands of separate relays, counters, timers and data storage locations. These internal relays are stimulated through bit locations in register. You can see the input circuit here and CPU, memory, output circuit. So input relays, counters, output relays, so internal utility relays, timers and data storage locations. First we will take input relays. So input relays also called contacts. So these are connected to outside world. So they are physically exist and receive signals from switches, sensors, etc. Okay, so input relays, that is input relays. First we will take that is input relays. Input relays also called a contacts. These are connected to the outside world. So these are connecting to the outside world. They physically exist and receives signals from switches, sensors, etc. Typically they are not relays but are going to be transistors. So next is internal utility relays. So these are do not exist. These do not receive signals from outside world, nor do they physically exist. So okay, they do not receive signals from the outside world. We have to get the difference between the input relays and utility relays. They do not receive signals from outside world. They are stimulated relays are there are also some special relays. Okay, so now this is going. So again, do not physically exist. Next is a counters. Counters do not physically exist. They are stimulated counters. They can be programmed to count pulses. Okay, so typically these counters can be maybe up down count or down count. Okay, okay, so or both. So it may be up count or down count or up down or both. So these are stimulated, they are limited to their counting speed. Okay, so this is what PLC. We will discuss the PLC in the next class, that is its structure as well as its operation and relays. Okay, if you have any doubt, you can ask. We have less than 1 minute time. So otherwise, so that is the time is up, and syllabus for the test will classroom.